Can you respond? No response. अरे yes, no, कुछ तो बताओ. Can you hear?
Yes, sir.
Can you hear me? Can you tell whether you have any doubt? Yes, no,
No, sir. No doubt.
no doubt. Good. As usual, there is no doubt. Achha. Okay, so as you have no doubt and imagining that you understood all whatever I discussed in the last few classes, so let me move to the next topic that we'll discuss PN junction. And this about PN junction already you have some idea about the junction uh, and maybe you may have some idea about its characteristics, right? Today we'll start it and we'll see the junction characteristics, its formations, and its the uh, transport phenomena of the carriers, charge carriers in the PN junction in presence of like bias potential or without any bias potential that we'll see. Okay, so let me first show you the Venn diagram and the charge distribution in the bulk semiconductor that already I told you, and from this picture it will be more clear to you how the different charges are distributed, that is the free charge carriers as well as the immobile charges, and also it's the charge neutrality formula that I told you how the charge neutrality is maintained. So now if you see here, first, what is there? This is the, can you tell this band diagram is for which type of semiconductor and this band diagram is for which type of semiconductor? Can you respond?
The first one is for p-type.
Huh? Bola?
The first one is for p-type.
First one is for P type and this one is for, this is for
N-type.
P type. Good. P type and this is for N type. How could you recognize that it is for P type and N type? It is for N type.
The Fermi energy level and that after the doping that energy level.
Fermi
That
energy level. So this pink color, a pink color line, this pink color dotted line, this represent what? Fermi energy for intrinsic semiconductor, right? And this is after doping, it is shifted towards the valence band energy. So this is what PF after doping, and that is shifting towards the valence band. That indicates that more holes are there. So this indicates it's a p-type semiconductor, and that appears due to doping. Similarly, it is intrinsic Fermi energy level, and it is moved towards the conduction band. And this indicates that the donor atoms provides the electrons, more electrons are there, and that leads to move the Fermi energy towards the conduction band. Okay, so now again here in p-type semiconductor, what are the different charge carriers are there? And what are the different actually charged particles are there both in p type and n type? First, let us see what p type. This negative sign encircled with this, the negative sign encircled negative sign, this indicate what? And this plus sign, this indicate what? The plus sign, this indicates the generation of holes. These are the holes. Okay. And this negative sign, encircled negative sign, minus sign, this indicates what? Can you tell? These are
Electrons.
no encircled
Ionized
minus
atoms.
ionized acceptor atoms. Ionized acceptor atoms. Okay. And this plus sign, this represent volts. That means what? Whenever in p-type semiconductor you are doping with the atoms of periodic table G, there is a deficiency of one electrons to form covalent bond. To form the covalent bond, 4 electrons are there in the original atoms of silicon and germanium. Rather, whenever you are replacing that silicon or germanium with one atoms of periodic table G, it has only 3 electrons, so it has a deficiency of 1 electrons, and that creates one holes. Okay, so these are the plus sign holes represent, these are the free holes. And encircle minus sign, this represents that whenever the hole such deficiency of 1 electrons, then it can accept 1 electron from any other neighboring atoms by breaking the covalent bond, because there are so many atoms are there, germanium atoms, and with respect to that, only few atoms are replaced. That I told you that in the doping means in 10 to the power 9 atoms, the lighter doping. In lighter doping, the 10 to the power 9 germanium or silicon atom, in 10 to the power 9 germanium or silicon atom, 10 to the power 8 to 9 germanium or silicon atom, this only one the impurity atoms, only one impurity atoms are there. Okay, only one impurity atoms are there in 10 to the power 8 to 9 germanium or silicon atom. Okay, this is for lighter doping. And for higher doping case, in 10 to the power 3, okay, to 10 to the power 4, 10 to the power 3 to 4, that germanium or silicon atoms, only one impurity atoms are there. That means aluminium, boron, it may be. Are you getting this? So so what does it indicate? That means if you consider there is a doping atom, say aluminium is there, okay. So surrounding this, there must be several germanium atoms in the crystal structure. Several germanium atoms. So this indicates that whenever there is one deficiency of one electrons, so it can accept the electrons from nearby neighboring atoms, any one of these. It can accept an electrons, and it will be negatively ionized after accepting it. So this indicates one deficiency of electrons represent indicates that there is a hole. So and that's why this type of negatively ionized atoms are there, and also the free carrier holes are there for p-type semiconductor. In n-type semiconductor, what you can see? What are there? You tell me. Response quickly. In n-type semiconductor, what are the different charge carriers or charge particles?
Electrons.
Electrons. So from this diagram, what should be the electrons? What indicates the electrons? So this negative
Minus.
sign, yes, minus sign represent these are the free electrons, and that are obtained by the or with the help of externally doping atom, that is donor types atoms, right? It may be phosphorus, or it may be uh, uh, for n-type semiconductor, right? Are you getting it?
Yes, sir.
Okay. So whenever it donating an electron, for the case of n-type semiconductor, there five electrons are there. So whenever it providing one electrons, say if we consider this is phosphorus, then one after giving one electron, so what will happen? It will be positively ionized, and these electrons now free to carry the current, and it can combine with any other uh, it can carry the current actually. And whenever there is some other position to be recombined, also it may recombine, or vacant position may be filled. So accordingly, there is a movement of the electron is possible with the help of drift current, with the help of external applied field. So what are the different charge particles are there in n-type semiconductor? So these are ionized donor atoms, donor atoms, and these are the free electron, that is the free electrons. So now from this discussion, what different charged particles that you can get for care to conduct the current, that already you know. Once again, I am repeating it because don't be confused, and still some of the students will do this mistake, that both all these will be carrying current. That is, the ionized atom, donor atoms, ionized acceptor atoms, all these will be confused with electron holes as well as the ionized acceptor and donor atoms. So here don't be confused. These acceptor ionized atoms or ionized donor atoms, these cannot contribute any current because these are stationary. This in the atomic crystal position, these are fixed. Their mass is very high. So with the help of external field, it is very difficult to move their position as compared to the movement of the free electrons or holes. So that's why the current is only due to these free electrons and holes. Okay. So these are the two concept of different charge particles in isolated P-type semiconductor and N-type semiconductor. Now, if we see in terms of the number of charged particles present there in N and P-type semiconductor, from this you will get an idea. For P-type semiconductor, this is P-type semiconductor. What are the different charged particles are there? What are the different charged particles are there for P-type semiconductor? You tell me. Charge carriers. Positive charge carriers or negative charge carriers are there in
Majority of holes
Positive.
and less number of electrons.
Yes,
Positive.
positive.
positive. Good. In p-type semiconductors, so this indicates what this blue color represent, as it is represented with blue color as you can see, and the red color represent the negative charge particles. So this blue color represent here in p-type semiconductor mostly due to holes, and accordingly mostly the positive charge carriers are there as compared to and also you know that though in p-type semiconductor mostly the majority carriers are holes, but still there are some minority carriers that should be there, though in this diagram it is not indicated or shown here. In this diagram you cannot find any electrons, 3 electrons, but still there must be some free electrons as well as holes are there that would be generated due to the intrinsic property of the semiconductor, or due to the thermal electron hole pair generation due to temperature. Okay. So that's why there must be some of this plus sign that indicates the holes and some of the minus sign to indicates the electron. There must, you have to represent that. these to indicate you, these to indicate that it's the electron hole pair generation pairwise due to the jumping of the electron from valence band to conduction band, or due to the breaking of some covalent bonding. Okay. So that's why what you can see in p-type semiconductor, mostly the positive charge and very less as compared to that, very less minus charge, negative sign, that is the negative charges are there. So can you see in this diagram? Can you understand here?
Yes, sir.
Yes, sir.
Okay. And now similarly, you see for the for the case of n-type semiconductor, that also you can see here what would happen for n-type semiconductor. Mostly, what the charge carriers will be there. What type of charges?
Negative.
Negative charges would be there. So accordingly, you can see the mostly negative charges are there, and as compared to that, very few positive compared to that, very less or few amount of negative charges are there, and a positive charges are there. That is what the due to minority carriers. Here, mostly negative. Okay. Mostly negative charges are there. Okay. Similar, these are the free charge carriers or charge particles, free charge particles that contribute current. Now, if we consider the in terms of doping, in p-type semiconductor, ND after providing or after donating an electron, ND becomes positively ionized. So, will you get the donor types or positively ionized atoms in the p side? Will you get it?
No, sir.
Uh-huh.
No, sir.
In the p side, will you get any dopant, any donor types atoms, ionized donor types atom in the p type semiconductor?
No, sir.
No, sir.
No, because in p-type semiconductor, the ionized atoms, you are doping with the atoms of periodic table 3, which after accepting an electron, it will be negatively ionized. Are you getting it? So
Yes,
accordingly,
sir.
in the p side, you cannot get any Nd plus. That means ionized donor atoms. Ionized donor atoms only will be available where? In n-type semiconductor. So accordingly, you can see here there is no such donor atoms. Just to give an idea, and this picture will help you to understand how the different donors and the free carriers are distributed throughout the semiconductor. Okay. So are you getting it?
Yes,
Okay.
sir.
Yes.
Now in
Yes, sir.
p-type semiconductor, similarly, in negatively ionized acceptor atoms, where you will get and how it will be distributed. So these acceptor types atoms, ionized atoms, that mostly and that is distributed uniformly throughout the p-type semiconductor, and that's why this is uniformly distributed like this. And also, look at this in the n-type semiconductor, there is no such natively ionized acceptor atoms in n-type semiconductor, and that is represented, indicated here. Okay. And another interesting point to note here, look at this here. But in p-type semiconductor, as you can see, the area, total area of holes, this total area of holes in the p-type semiconductor, that is equal to the total area of the negatively ionized acceptor atoms. So what does it indicate from here? Can you tell?
Net charge is 0.
What does it indicate? Hmm? What does it indicate? So this bolo.
The total charge will be 0.
Total charge will be 0. Good. Actually, in P side, you are getting the holes, due to the doping of the acceptor types atoms, right? Acceptor types, P types atoms, that is the atoms from periodic table C. And also you will get the electron hole pair generation, that is due to thermal generation of the electron hole pair. So there are charges will be due to this, both of these holes. That means the holes, this should be, this must be equal to the total area that electrons due to the minority carriers, thermal generation, as well as the negatively ionized atoms. So this total area should be equal to this, because holes contains, this is contributed by the acceptor atoms as well as the thermal generation of the holes, and this is what the electrons, that is the thermal generation as well as thermal generation as well as the acceptor atoms, ionized acceptor atoms. So okay, similarly here in n-type semiconductor, you can see that the total uh, area of the positively ionized, positive charge carriers, that is the donor atoms, and the thermally generated minority carriers holes. These two area must be equal to the total area here, that is due to the electron. That this indicates the charge neutrality formula, and accordingly, if we want to get the total charge in the semiconductor, that would be what? You think and you tell me what would be the total net resultant charges in isolated semiconductor as well as in isolated p-type and n-type semiconductor. Can you tell what would be the total charges?
0.
0.
That should be 0.
Zero.
So don't be confused, and uh, don't, you should not have any or any confusing idea that as n-type semiconductor mostly consisting of the free electrons, so it is overall it is negatively it contains the negative charge, or it is the negatively charged, more accumulation of the negative charges are there. And also the reverse case for the p-type semiconductor, it is positive charge which consists of this. So don't, like, it is not like that. The as per the charge neutrality formula, and also if you see, if you try to, if you see in details, in depth, then you can understand that it contains both negative as well as the positive charges are there uh, in both type of semiconductor, in n-type and p-type, and net the amount of charges could be zero. Only the difference is that for p-type semiconductor, the only in both n and p-type semiconductor, though both type of charges are there equal and opposite, but one type of charge particles only carries the current or help to increase the conductivity. So that for p-type, the holes are free, that can contribute the current, and for n-type, only the electrons can contribute the current. So these are the things that you should understand well. Okay. Now let us try to understand what will happen. This is so far I discussed with the isolated semiconductor bar. Two types of semiconductor bar. One is n-type, another is p-type. Now let us see what will happen if we join these two isolated semiconductor bar. If we just join side by side. So just here in this context, let me tell you that though this joining is not so simple, that if we that by taking two bulk semiconductor it is joined together. It is not such simple process, but there is some mechanism by which this doping is done to form PN junction. Okay. Um, Actually, actually how this PN junction is formed? Just let me introduce you it. Otherwise, you may not be clearly understand it. Uh, First, is semiconductor bar is taken. A intrinsic semiconductor bar is taken. Okay, to form a PN junction, right? And after taking one intrinsic semiconductor bar on this side, the side in which or the region on which we have to we want to dope with or we want to make p side, and the side that we want to make the n type here, uh, uh, just doping is the atoms are doped by deposition method. That is what the here the aluminum or boron, that is the atoms from periodic table 3, that's are deposited. Okay, and here the atoms of periodic table 5, that's are deposited in this side. Okay, these are by using some ion implantation method or thermal evaporation deposition method. The different method is followed there. Okay, so this is not like that the separated or isolated semiconductor bar that we are taking or we are joining together, and that will see this will not give or help us to give the junction property. That we will see and you will understand. You will tell me, you will answer me why that will not happen after discussing or at the end of this class. Okay, just let us see here. Uh, if we place this PN junction, what will happen initially? Initially, if you see here that this is what the Fermi energy in the N-type semiconductor. Here, this side is N side and this is P side. Okay, so in that case, what would be this? The Fermi energy, as you can see here, in the N side, this is close to the conduction band, and in the P side, it is close to the valence band. That already you know. So according to what you can see, just at the junction, there is a abrupt change in the Fermi energy. Okay, abrupt change in the Fermi energy. But if we want to make a system, the Fermi energy should be is one energy level, and that should be same throughout the system. Just try to understand. The Fermi energy is a single energy level. Are you getting my points? It's single energy level that defines that it's energy level at which the probability of occupancy of an electron is half, right? So accordingly, if we consider a system that represents only one energy level, and whenever we make the system, then this energy level, these two will combine and make one energy level. But here there is an abrupt junction, a abrupt change in the Fermi energy. And also this type of junction is known as the abrupt junction. Abrupt junction is why? Because here if you see the doping concentration with respect to the junction, here the doping concentration is 1, that is for p-type semiconductor. Here the doping concentration is for another, and that is uniformly in the n-type semiconductor. Okay, these two value, that is the doping concentration value, these two are different, and different types of doping materials are there. Okay, and these are changing abruptly. This is changing abruptly. That's why it is also called the abrupt step index junction. Okay. Okay. So this is what how the junction is formed. Now let us see in details after forming the junction what will happen. As already I told you, in the P side, what would be the different types of charged particles in the P side? That also already I told you, and also in N type, what would be the in N type semiconductor, what are the different types of charged particles are there? That also you know. So what are there? Just to remind you how yeah, you understood? Just can you tell in the p-type semiconductor what are the different charged particles are there? Anyone can you tell? Huh?
Mostly the holes and less number of free electrons.
बोलो बोलो.
Mostly the holes in p-type
हाँ, हाँ.
and less number of free electrons.
3 electrons and others.
Acceptor ions.
Ionized
Yes,
acceptor.
I asked you to say the charged particles. Okay, charged particles may be the free holes, maybe the ionized atoms, and also the less number of electrons. So that you have to mention that. And it is very important to remember, p-type semiconductor, not only there the free holes, also there the ionized atoms are there and almost equal number. And similarly in n-type semiconductor, though free electrons are there, very large number of electrons and also almost equal number of ionized atoms are there, donor atoms. So in n-type semiconductor also you will remember these atoms are positively charged ionized atoms because after donating an electrons, effectively the atom is neutral initially, but whenever it is leaving an electron, it is donating an electron, it is getting positively ionized. Okay, and similarly for the acceptor types atoms, initially it is neutral, but whenever it is accepting an electrons, so it is getting negatively ionized. That you should remember. It is leaving electrons, getting positively ionized. It is accepting electrons and getting positively, negatively ionized here. Okay. So now, with this, just you see how the holes are distributed. Holes being the positive charge particles. This plus symbol represent to indicate you that it is a positive charge carriers. Okay, it carries the positive charge, the holes. So can you see the distribution here in the p side? The p side, mostly the holes are there, and accordingly the holes will be more. And in the n side, the number of holes are very less. Can you see here in this diagram? Do you understand it?
Yes, sir.
Can you understand?
Yes,
Yes, sir.
Okay.
yes, sir.
So similarly, can you see for the electron distribution throughout the semiconductor? Look at this here. In the p side, the electrons are very less, and in the n side, the mostly electrons. Accordingly, electrons are more. And also note here the change in the concentration of the holes and electrons. Similarly, if we see here the donor atoms, distribution of the donor atoms that carries the positive charges. Okay, this look at this. The donor atoms should not be there in the p-type semiconductor. Only it is uniformly distributed throughout the n-type semiconductor. And here for p-type semiconductor, what would be the acceptor atoms? The distribution of the acceptor atoms should be like this. It is uniformly distributed. And also just up to the junction, and after the junction there should not be any acceptor atoms. So now with this distribution of the charge carriers after forming the junction initially, what we can see here, there is we can see that there is the change in carrier concentration from p side to n side, that is for hole, and also for electrons. Also you can see in the n side the electrons are more, and in the p side electrons are less. Okay, and also you can see here in the n side the ionized donor atoms, distribution of the donor atoms, these are very high as compared to the acceptor atoms. In the p side there is actually no such the donor atoms, similar to here. So what does it indicate? It indicates that infinite infinite hole gradient, infinite electron gradient, infinite donor atom gradient, infinite acceptor atom gradient just at the junction. Okay, so gradient means what? Actually changing the carrier, changing the concentration of the such particles. Say it may be dndx, it may be dpdx, it may be dndx, it may be dnadx. Just at the junction. Are you getting it?
Yes, sir.
Are you getting
Yes,
it? Yes or no?
Yes, sir.
Yes.
Okay. So if you understood, now you will help me by telling what would be the total charge throughout the semiconductor or throughout the junction. What would be its total charge? What would be the total amount of charges?
0.
0.
the zero.
Zero.
Neutral.
That already initially I told you, because always there is no bias potential external. The charges are not coming from anywhere. It is whatever they are within the semiconductor. Okay, bulk semiconductor. So only it would be if it is positively ionized, then that means there is must be equal number of electrons are there to give the negative charges. Okay, so that indicates the total charges throughout the semiconductor where that should be 0. Now let's see what happens if there is after forming the junction. Just it is what happens, the scenario after forming the junction, actual scenario that is depicted pictorially here to understand better. Now, you tell me, as there is a change in gradient, what would happen? What phenomena you should get? You should observe. Response quickly.
Diffusion of flow
Yes.
of current.
Diffusion. Good. Diffusion, what do you mean by diffusion? That already you know that if there is a gradient, concentration gradient, okay, then the particles will move from higher concentrated area towards the lower concentration area to make it uniform distribution. This is what diffusion that I told you. And also you know. Okay. So accordingly, what can we expect from here? You tell me. What can we expect? Can you tell?
There
Yes,
is some
sir.
flow of current.
बोलो 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 जल्दी.
Holes from P-type can flow into N-type semiconductor, and electrons from N-type semiconductor is flows into P-type semiconductor.
Good. So the holes from P to N, and because holes and electrons are the movable, but these are the atoms, ionized atoms, the donor atoms or acceptor atoms. These are not actually movable. These are stationary because these form the crystal structure. If we see the crystal structure, the atomic structures are like this. Are you getting my points? So this you cannot dislocate the atom from here. Only it can provide the electrons or it can carry an electron to make a hole. It can attract an electron and combine one, accept an electron only to form the positive or negatively charged ionized atoms. Okay, but it cannot move. Only what will move? Here, these free carriers, that is the holes from P side to N side and electrons from N side to P side, and that is due to the presence of this gradient node here, not due to, and don't write this, then you will get big zero. that it is due to the same type of charged particles, the repulsive force, Coulomb's repulsive force due to Coulomb's law. That is the same type of charges are present there. That's why the electrons from n side moving towards the p side and holes from p side moving towards n side. It is moving due to why? Why it is moving? Tell.
The concentration gradient.
Concentration gradient, and that is because of diffusion. Okay. So then what we can see here now, the we have not applied any bias. That is continuous. So what would happen? There is a whole gradient in the junction. So accordingly, there would be diffusion, and we will get, due to diffusion of the carriers, what we can get? The diffusion current, and that would be what? Diffusion current. Are you getting it?
Yes, sir.
Okay. So this is what already I told you in the last class, the diffusion effect and the diffusion current. So now holes due to diffusion, holes entering into the p side, and whenever holes are entering in the p side, and similarly also the electrons from n side, it will be entering into the p side, and also due to diffusion, what we will get? This is what diffusion current density. This is what diffusion current density due to holes, and this is for electrons. So here, from here, huge holes will be diffused towards the n side. Here, the huge electrons will be diffused from n to p side. Is it clear? Now, so far up to this is clear to you?
Yes,
Yes or no? Okay.
Yes, sir.
So, okay.
Yes, sir.
So if you understood it, now look at this. Whenever the holes are coming to the n side, in the n side there is huge number of electrons. And similarly, whenever the electrons are moving towards the p side, there is huge number of holes are there. So accordingly, the holes reaching to the n side, it will be recombined. That means it will be lost. Similarly, electrons just reaching towards the p side, it will recombine with the holes, and accordingly it will be lost. Okay. Again, another interesting thing is that whenever the electrons is moving, electron is generated due to because of, you tell me, and how the holes are generated. Just you remember the original form of generation of the holes and electrons in n type and p type. In p type, the holes are generated due to, and electrons are generated due to in n type. You tell me how the holes are you are getting. You tell what are the decomposition of this, and what is the cause of getting the holes. You tell.
Because of doping of some atoms of valency 3.
Valence 3. That means there is one deficiency of electrons. So it is accepting one electrons. In p type, accepting an electrons, that's why we are getting holes. Are you getting? And n type,
Yes,
there
Yes,
is
sir.
a deficiency of electrons. So it is accepting an electrons, it is providing holes. So whenever these holes are moving towards this, just I am telling you by considering one example so that you can understand. There are such huge number of such holes and ionized
Sir,
accepting atoms are there. Bolo?
sir, whenever doped with 3 valence electrons, how many electrons are accepted by it, sir? From silicon?
How many? No,
Electrons.
in the valence bands, there are 3 electrons. If you see covalent bond structure for germanium and silicon, if you consider germanium, in germanium, there are 4 outer valence electrons in the outermost orbit. That means the 4 valence electrons are there. So what happens it share with 4 nearest neighboring electrons to form the inert gas like atomic structure or to make it stable atomic structure. Okay, so that's why it is shared with 4 nearest neighboring atoms like this, and these are called the covalent bonding. Covalent bond. These are called. So here actually one electron from this atom, another electrons from another nearest neighboring atom. And similarly for all other, this is the what the crystal structure of both germanium and silicon. This you should understand first, then you will be able to understand other things. Okay, all these are germanium or silicon. Now you got it? So whenever we are donating, we are doping with some other atom like aluminium or boron, it has 3 outermost 3 valence electron. That means we need 4, but here 1 electron is deficiency, has deficiency. If you consider it is aluminium, it has 1 deficiency of electron. So this covalent bond is not completed. Okay, so it has that means there is 1 deficiency of electrons. So actually, effectively, what happens? That indicates that it is it like a hole. Okay, so just these holes. That means this for the as the aluminium can have the tendency to accept 1 electron, so this electron it can take from its neighboring atom. And after accepting these electrons, it is getting negatively ionized. So that is what the negatively ionized atoms. And whenever these electrons are coming here, so it is forming 1 electron holes. Okay, just like this is holes. Okay. Are you getting it now?
Yes, sir.
Okay. So now whenever these holes are moving towards the n side, so what is left behind in the p side? You tell me. Now these holes coming here. You tell me what is left behind it. So now what is left behind? The ionized acceptor atoms are there. It is left behind. Similarly, whenever the donor atoms donating an electrons, it is positively ionized. And when these electrons, I am giving solid dot to represent the electrons. And when this electron coming towards the p side, then this electrons is coming towards this, then what will happen? So it left behind 1 positively ionized donor atoms. Are you getting it?
Yes, sir.
Yes, sir.
Okay. So then as it in a resultant, what we'll get in the n side, just near to the junction, whenever the electrons are moving towards this, it is recombined and lost, and it left behind the positively ionized donor atoms. And similarly, whenever holes are moving towards the n side and recombine, and it is leaving behind the ionized acceptor atoms, negatively ionized acceptor atoms. So now near to the junction, as you can see, this is what an uncompensated ionized positive atoms and ionized acceptor, negatively ionized acceptor atoms are there. Are you getting it? There is no such carriers because already it is recombined and lost on either side. And this is what is called, this region is depleted. This region is depleted from free carriers because holes from here already it has crossed, moved towards the n side and recombined and lost, and electrons from here already it is moved towards this side and recombined with the holes and lost. So now near to the junction we are getting this uncompensated the space charge region. Space charge, this is what is called space charge region, because within this space we are getting the immobile ionized atoms, and also this region are depleted. The term is depleted, and that's why it is called depletion region. This is what is called depletion region. depletion region. Okay. Now what we can see from this diagram, so as there is no such things and it is like a battery. Okay, on either side there is the on the two sides the two opposite charges are accumulated and it forms a built-in potential that you can see that the potential will be directed from positive to negative, and this electric field, it will develop an electric field, and this electric field will oppose the further movement of the electrons and holes to cross the junction, and because the movement of the carrier due to this gradient cannot be in for infinite time, it will be stopped under equilibrium condition. And what is that equilibrium condition? That is an built-in potential will be developed just near in the junction, near to surrounding the junction due to the depletion region, and this built-in potential will the field, the electric field due to this built-in potential will be directed in such a way that it will prevent further movement of the electrons and holes. And whenever this built-in potential is sufficient enough to further movement of the electrons and holes, then the equilibrium condition will be reached. Okay, and this is what the diagram of the built-in potential that represent the potential energy is in the N side it is positive, that is higher potential. In the P side it is negative, that is lower potential. And we can prove it. This can be proved. The detailed proof is not required. The derivation that this built-in potential is given by VBI is equal to KT by Q. K is the Boltzmann constant, T is the absolute temperature, and Q is the electronic charge, is equal to KT by Q dot ln NA by Ni square. What is Na? Na is the acceptor atom concentration. It is the concentration of the donor atoms. Ni is the intrinsic carrier concentration. Okay, so this is what the formation of the built-in potential or the barrier potential. So now could you understand what do you mean by this barrier potential or built-in potential?
Yes, sir.
Okay,
Yes, sir.
and you could understand what is depletion region, what is diffusion there in the after formation of the PN junction. This is very important to understand as well as later on to explain any characteristics, this junction behavior and the actual construction of this junction in depth you should understand first. And once you understand in the beginning, then it will be easier to follow the classes and analysis throughout the class, throughout all the lecture and the course. So do we have the class from 10? Do you have class from 10?
Yes, sir.
Okay. So then let me stop here. Before closing this, we'll discuss the junction with bias in the next class. So before stopping it, just let me ask if you have any queries or any doubt. Let me clear. Have any queries? You must respond.
No, sir.
Do you have any queries?
No, sir.
Himanshu?
No, sir.
No, sir.
Himanshu? Himanshu Kumar Saha? Himanshu Kumar Saha?
Yes, sir.
What are you doing? Are you attentive in the class?
Yes, sir.
But how? Anyway, could you understand whatever I taught?
Yes, sir.
Okay. Thank you. In the next class, I will ask you the question.
Thank
You
you.
understood, be prepared.
Okay.
Okay?
Okay, sir.
Okay. Okay. Thank
Sir,
you all. हाँ बोलो.
sir, please recommend a book for this.
Okay, I'll share it in MS Teams
Okay, thank you, sir.
in my lecture PPT.
Thank you.
Okay.
Thank you, sir.
Already it is shared in the
Thank you, sir.
lecture PPT. You go through this. It is shared in the beginning. After discussing the detailed syllabus, all the textbooks, reference books, all are given. Okay. You can follow the book by Boyle State. You can follow the book by Milman Halkias, Chattopadhyay Rohit. Any standard textbook, what are given there, any one you can follow in the beginning. Okay.
Thank you, sir.
Okay, sir.
Yes. Thank you all.
Thank you, sir.
Thank you all.